Okay, cool. So let's get started. We're going to cover yet another exciting topic. For some reason, all the topics in this course are quite exciting. Hopefully, a lot of people share my excitement. We're going to talk more about microarchitecture. We did talk a little bit about microarchitecture when we talked about the ISA and the von Neumann model, etc. last week. Today, we're going to start with a more in-depth treatment of microarchitecture. So hopefully it will not be unfamiliar to many of you who've been following. And then we're going to continue next week. Tomorrow, there's no lecture, as you know, due to the Easter break. But we will pick it up after the Easter. Okay, so this is what we intend to cover. Today, we're going to do microarchitecture and single cycle microarchitecture. So those are the readings, and I'm going to reference them. And multi-cycle we will cover after the Easter break. But we will today I will also mention what multi-cycle is. And then after that, we will do pipelining and pipelining issues and go deeper into how to improve the performance of a sequential execution engine. And this is a view of our agenda. Basically, we covered ISA assembly programming last week, and we're doing microarchitecture right now. And then we're going to do more microarchitecture, basically, essentially in the next few lectures, multi-cycle microarchitecture, and then improve its performance with pipelining. We're going to discuss a lot of really interesting issues in pipelining, how to handle control and data dependencies, how to maintain state, how to recover state when you have exceptions or branch mispredictions, for example. So a lot of state-of-the-art techniques will be covered. And then we will move to out-of-order execution, basically where we will violate the sequential execution principle, but not expose it to the programmer. So hopefully it's going to be fun. And we're going to really cover what existing architectures do today. So we're building up to that still, basically. Still, we're at baby steps. We're still not at today yet. So recall, we introduced the von Neumann model last week, and hopefully you know exactly what that is. It has 5 components. And we also talked about the von Neumann machine, an example von Neumann machine. LC3 was one example, MIPS was another example. And we've started studying both examples, if you recall. And we also talked about the instruction cycle. Basically, an instruction goes through multiple stages of processing. It gets fetched, decoded, evaluates its address, fetches its operands, executes, and stores result. We're going to talk about that. And then you fetch the next instruction, basically. That's the principle of sequential execution. And we're going to see more of this instruction cycle today to build our single cycle microarchitecture. And recall, we talked about instruction set architecture in some detail last time. Today, we're going to actually start a little bit more with the instruction set architecture because I want to challenge you to think a little bit more critically than what we have seen so far, so that you don't think that the von Neumann model is the only model for building computers or processing programs or executing instructions. But before that, let me talk about microarchitecture a little bit. So microarchitecture, as we also discussed before, is one implementation of the ISA. So instruction set architecture is what gets exposed to the programmer. It's the hardware-software interface, what the hardware promises to deliver to the programmer or the software. And microarchitecture is what implements that promise, essentially. As a result, it could be done in many ways. As long as you implement the promise, it doesn't matter how you do it, basically. Let me put it bluntly that way. That's how it is, actually. So the question is basically, how do we implement the ISA? And we will discuss this for many lectures, as I mentioned. And there can be many implementations of the same ISA for the reason that I just said. There may be many ways of doing the same thing, satisfying the promise or the contract that you promise to the software, right? Okay, so for example, the MIPS ISA that we studied has many implementations. It started with R2000, for example, and one of its latest implementations is R10000, which can execute instructions out of order underneath. x86 has many implementations. I don't even put the 8086, for example, here, but 486 was one of the first machines that I owned, actually. And then Pentium Pro. Right now, I think the latest one may be Comet Lake, but don't quote me on it because Intel comes out with a new Lake every half a year or so, or every year or so these days. And then AMD also has its own implementations, as you know. And these are all part of the same ISA. Of course, it's not exactly the same ISA because ISAs over time evolve as well. And we will discuss this because they incorporate new instructions, for example, so that they can cater for new workloads. But they don't change as fast as microarchitectures because they're what's exposed to the software, right? Microarchitecture doesn't get exposed to the software, so it can change quite often without software changing. IBM has the Power PC ISA, for example, or Power ISA, and it has many incarnations. Recently, there's also the older Power PC processors like 604. ARM has many possible implementations done by many different folks, done by ARM, for example, done by NVIDIA, done by Apple. These are all the same ISA, give or take some instructions, of course, right? Again, ISAs evolve, but fundamentally, the ISA is the same that is implemented by these processors. Alpha, which is a dead ISA, which we discussed earlier, it's actually a very nice, clean ISA, and it has also many implementations, as you can see over here. And I didn't bother putting RISC-V over here because RISC-V actually has lots of implementations today because it's open source, right? So before we go more into microarchitecture, what differs between these microarchitectures is really how they implement the ISA. And we're going to look at the nuances in those implementations, and they're going to be big, basically, in terms of their performance, energy, power implications. But before I go into it, let me challenge you, as I said, a bit more. Let's talk a little bit more on ISA design as trade-offs. We talked about ISA trade-offs a little bit in the last lecture, and I referred you to some earlier lectures, some videos actually, to take a look more. But I'm going to talk about a key design trade-off in an ISA, which is really the processing model. And we assume that we have a one Neumann model, one Neumann architecture, and if you recall, it's also called the stored program computer, and it has two key properties: stored program and sequential instruction processing. Right. So we're going to deconstruct that soon. But before we deconstruct that, let's talk a little bit more about the one Neumann model. That's going to be important for later microarchitecture discussion. So stored program means instructions are stored in a linear memory array, and memory is unified between instructions and data. There's no distinction between them. If you just look at memory, for example, a memory location contains some bits, and it could be instructions, it could be data. And the difference is that when they're interpreted, basically the interpretation of a stored value depends on the control signals. Whether you interpret a stored value as an instruction or a data depends on when you actually interpret it. So the question maybe I will pose to you is, when is a value that you read from memory interpreted as an instruction? And if you want to answer this, you should think about the instruction processing cycle that we saw earlier, right? So if you go back to the instruction processing cycle, there are 6 stages in processing. And whether a value fetched from memory is interpreted as an instruction depends on when that value is fetched in the instruction processing cycle. So there are 2 places in this 6-phase instruction cycle where memory is accessed. One is the fetch part, and fetch is really specifically, you take the program counter, and the program counter points to a memory location, and you read that memory location and take the data out of that memory location and store it into the instruction register. Essentially, what you're doing here is you're interpreting the memory value that you read as an instruction. That's why it is an instruction, basically. Okay. And then there's another place where we actually access memory, which is the fetch operands phase. Some instructions access memory in fetch operands, for example, loads. And when you do that, basically, you take an address that's generated by the load execution, as we will see today, but we also saw last time, but we will see even more today when we talk about the microarchitecture. And then you access memory, or the processor accesses memory. And at that point, you interpret the memory value as data because you take that data value and store it into a register, right? You don't put it into the instruction register. You put it into a general purpose register. So basically, these 2 stages in the instruction processing cycle happen at different times, and they lead to different control signals. If you remember the control signals from last time, the fetch stage loads the value that is out of the memory data register into the instruction register, whereas fetch operands takes the value that's in the memory data register and puts it into a general purpose register. So how you interpret the value that you fetch from memory very much depends on which part of the instruction processing cycle you're accessing memory, and that is determined by your control signals. Okay, that's the stored program, and that's the distinction between instructions and data. Now, there's a question, I think, that says, is it a good idea to separate instructions from data? Yes, there could be certainly security benefits for that purpose. I'm not going to go into the details of it, but existing systems distinguish them in some way. So they, for example, we'll talk about virtual memory toward the end of this course. You can mark some pages, some regions of memory as executable versus not executable. That way, you're saying basically the executable part is really where your code is, or you have permissions to execute that code, for example, and that enables you some security benefits than blindly not distinguishing between instructions and data. So that's a very good question overall. Okay, so that's the stored program notion. And the second notion is sequential instruction processing, which you hopefully remember. Basically, we process one instruction at a time, and the program counter or instruction pointer identifies the current instruction, and it's advanced sequentially, except for control transfer instructions. Basically, PCs are incremented by 1 or by 4, depending on whether your computer is byte addressable and how large your instructions are, essentially. Okay, so I'm not going to go through the details of it, but we're going to deconstruct it, as I said. The von Neumann model and architecture is covered in your readings, and also the von Neumann seminal reading, which I would recommend you to do if you have time, but you don't have to do it. But keep these two principles in mind: stored program and sequential instruction processing. And we also showed this picture, right? Okay, now let me raise the question: is this the only way that a computer can process computer programs? So remember that we said we want a model to process computer programs, and we said, okay, well, Neumann proposed a model, and these are the properties. But if we actually are critical, if we're thinking critically, we would ask this question that I just asked over here on the screen. And the answer would be no, basically. Clearly, you can imagine many, many different ways. And I'm going to give you one other way right now, which will hopefully be interesting. But I will give you a qualified answer also, no. But this way of processing, von Neumann model of processing, has been the dominant way, meaning the dominant paradigm for computing for decades and decades, for essentially more than 70 years or so, let's say. But maybe it's time to change some of that going into the future, given that we're having a lot of trouble with data movement, for example, and memory accesses, as we discussed earlier, and as we're going to discuss even more. But basically, if you remember the slide that I put up in one of the earlier lectures, we said in order to build a computer, we need an execution model for processing computer programs. What other possible execution models can there be? And I think this is a good idea for you to imagine. If we were in a physical class, we would actually talk about this. Unfortunately, we're not in a physical class. I wish I was telling you that the pandemic ended and we were going to meet in person today, but that would be a terrible April Fool's joke. Unfortunately, people have not prepared the right things so that we could do that today. But that's a different conversation. But if you were actually in person discussing this, then we would actually have brainstorming, and maybe some of you will say perhaps GPUs have a different execution model, right? And that may be true, actually. Actually, we will talk about GPUs later in this course, and they have some sort of execution model, and it's not necessarily perfectly von Neumann, right? But what happens is basically you're operating on many data elements at once, single instruction, multiple data, and many, many threads are executing at once. So in a sense, there is no sequential execution at that point. And that's correct, actually. It's a different execution model. But the fundamental part of the CPU, which is executing a single thread, is still von Neumann, actually. A single thread is still single instruction, basically, executed at a time. Okay, we're going to get back to that. But that's critical thinking also. You can say GPUs are a different model. And absolutely, that's true. But they build up on the von Neumann model to get to a different multi-threading engine. But I'm going to show you a completely different model right now, actually, not GPUs. Basically, a completely different model for processing computer programs. And that's going to be the data flow execution model of a computer. And let's basically talk about these two models. Von Neumann model, as we discussed, an instruction is fetched, executed in control flow order, as specified by the program counter. I like the name instruction pointer because you point to an instruction in memory, right? But program counter has been the dominant name. Fine, we're going to use them. But so if I use them interchangeably, think about program counters if you're more comfortable with program counter. But basically, you do sequential execution unless you have an explicit control flow instruction. Data flow model is completely different. Basically, you fetch and execute an instruction data flow order. There's no program order, basically. We got rid of the fundamental aspect of von Neumann model, right? There's no program counter. There's no instruction order. We just have a data flow order. What does that mean? An instruction gets fetched and executed when its operands are ready. Basically, the input values that it's going to operate on, when they become ready, then you go and fetch the instruction and execute it. Now, this sounds interesting, right? Because now you don't fetch an instruction, wait for the operands. Whenever the operands become ready, the instruction gets fetched. So data flows beautifully between instructions this way. And in other words, there's no program counter instruction pointer. Instruction ordering is really specified by the data flow dependence. So each instruction specifies, basically, you need to somehow, in this case, you need to somehow write your programs in a way such that each instruction specifies which other instruction should receive the result that this instruction is generating. So you need to connect the instructions in a data flow manner, as opposed to assuming a sequential execution model and registers, for example. So we're going to even get rid of registers in this case, as you will see in a little bit. In a data flow program or data flow model, an instruction can fire, meaning gets fetched and executed, whenever all of its operands are received from other instructions. We will see a pictorial representation of it also. So basically, in this model, potentially many instructions can execute at the same time, because many instructions operands may become ready concurrently at the same time. You don't have any control over it. There's no single program counter, basically. There's no let's say, conductor of the orchestra that says, okay, now you're going to execute. Now you're going to execute. There's no such thing. Instructions execute completely asynchronously. And this happens in a way based on the availability of their data. And this may basically depend on when their data becomes available. So potentially you can have tens of thousands of instructions executing concurrently, right? Because you're not limiting the instruction execution arbitrarily by a program counter. So essentially, because of this, it's inherently more parallel. And hopefully you can imagine that also right now. But let's take a look at a very simple program to begin our discussion. So this is a sequential program. It's written basically less than or equal to means assignment here. In this first line, you get v gets assigned to a plus b, and then w gets assigned to v times 2, and then x gets assigned to v minus w, and then y gets assigned to v plus w, and then z gets assigned to x times y. Basically, clearly there's a dependence over here, right? And this is inherently sequential. And somebody wrote this program because the model said, okay, you need to write instructions in sequential order. So what is the significance of the program order, though? If I ask you, again, if you were in class, maybe you would answer with some answers and say, this enables us to think more clearly. And maybe that's true, actually. Maybe you're thinking more clearly because you're putting one thing at a time. And maybe this makes your debugging easier. You make your you can look at this program and you can say, oh, the value of x at this point is expected to be this. You can more easily pinpoint what the value of x should be given inputs A and B, for example. And you can easily see that value. So that program order enables you to think maybe more easily, potentially, right? And then I will also ask, what is the significance of the storage locations? So assume that all of these are allocated to some registers. So you see V and W over here. But if you look at V and W, they're intermediate values, right? Assume that Z is the only output from this program, and you're going to print it somewhere, for example. V and W are really not important. They're intermediate values. The goal for these storage locations is just to store intermediate values, meaning they're to communicate between these instructions. So you generate A plus B, and the result needs to go here. You need to do A plus B minus B times 2. The result of A plus B needs to go here. The result of B times 2 needs to go here. And the result of X needs to go here. And A plus B also needs to go here. B times 2 needs to go also wherever W appears. So basically, the goal of these V, W, X, and Y, well, not X, X and Y are also intermediate variables, are really to communicate values that are produced in an intermediate manner, temporary manner, by instructions. So you don't need to waste registers for them in a sense, right? As we will see in the graph that I'm going to show you over here. So basically, you can express exactly the same thing with this picture. And this picture is a graphical picture that essentially shows the data flow between the operations. Imagine that each node is an instruction. So this is a plus. This is a times 2 instruction. Assume that somebody came up with that. This is a minus. This is a plus. And this is times, again, multiply. In fact, times 2 can be, an input can be tied into 2 over here, right? It can be a general multiplication. But essentially, these two are equivalent. Equivalent in the sense that they achieve the same purpose. You can see that inputs are A, B, output is Z. Intermediate values here are not stored anywhere. They just get communicated between these data flow nodes, right? So, but there's no program order here. If you look to the right, I actually wrote these, drew the graph in a nice way to show that which instructions can be executed in parallel. So you can see that this A plus B, as well as B times 2, can be executed completely in parallel. There's no need for a program counter. These two operations can be executed completely in parallel because V minus W and V plus W, clearly V and W are ready after these two are done. So you can see that we've connected these operations to each other based on which ones need, so this minus, for example, needs the value of a plus b as well as b times 2, right? Based on which values each node needs. And that's how we connected these nodes and formed a data flow graph. And this could be your program, essentially. You could actually program in this graphical language, let's say, and then give it to a computer or compile it down to something that expresses these things. And we will see some example graphical representations. And then the computer can simply execute those data flow nodes and fetch things when the inputs of the data flow nodes, each data flow node is available. So hopefully this is clear. Basically, you can also eliminate some registers because you don't need these registers, right? B and W, X and Y. They're just outputs of these instructions that are needed by some other instructions, but that are not needed to be stored later. Of course, you need to do the analysis to understand that they're not needed to be stored later. That way, you can get rid of the registers, and you just communicate the values to wires, for example. So you could imagine implementing this exact thing directly as gates exactly as logic gates on an FPGA, for example. That's why FPGAs are actually very good potential data flow engines. They don't have an ISA, right? You can directly implement a graphical data flow graph like this on an FPGA by programming the bits on an FPGA as you are doing in your labs. Okay, so this is important to distinguish, basically, and that's what I wanted to mention over here. We're going to see some trade-offs later on and talk a little bit more about data flow. But I will ask the question, which model is more natural to you as a programmer? Is it the sequential model or the data flow model? Who says sequential? Maybe people can raise hands. I don't know if I can see hands. I see some people. Okay, that's a lot of people. I'm not counting. Who says data flow, I guess? Okay, I see fewer hands with data flow as usual, but there are some hands. I hope they're not raising their hands for von Neumann and I'm interpreting them as data flow. But yes, usually it's the case that sequential is more natural to people because, I mean, this could be due to multiple reasons, because it's easy to follow clearly, but it could also be because of education, right? Because that's the model you've been used to. That was the model you've been taught, maybe in high school, but certainly in your programming classes here, right? And it's not the data flow model. But data flow model, I would argue, is potentially as equally simple, in my opinion, once you understand the power of it. And again, you can potentially think in parallel this way. And one of your fellow students says maybe humans cannot inherently think in parallel. I'm not sure about that. I don't know. I don't have enough knowledge to actually make a definitive statement about whether humans can think in parallel, because there's a lot that happens in our brain, right, in terms of parallelism, like vision processing, for example. Yeah, I'm not absolutely sure about that. So I think once you actually get trained in the data flow model, you can actually think about things as data flow graphs also, and it becomes beautiful, in my opinion. So it's good to, I think about anyway, stretch your boundaries, if you will. Let me put it that way. Okay, let's go a little bit more into stretching these boundaries. So in a data flow machine, a program consists of data flow nodes. So a data flow node fires or gets fetched and executed when all of its inputs are ready, meaning when all of its inputs and tokens. So this is terminology in data flow. You have a token in your input arcs, let's say. At that time, you can start executing the instruction or fetching and executing. So this requires that you need to represent each instruction as a data flow node and encode it some way, just like we've done. We've encoded other instructions like earlier, right, in the von Neumann model. So this is one encoding. Don't get stuck on the encoding too much in this case, but this is the data flow. This is the real instruction on the left side. It's a multiplication instruction. It has two inputs, left input and right input. And for it to fire, both inputs need to have tokens, need to have values. And when both inputs have values, then this instruction gets fetched and executed, and then it produces a token with meaning its result, essentially. So you can see that this is the encoding. It's a multiplication, and it has a left argument, and it has a ready bit for the left argument. Is it ready? It has a right argument. It has a ready bit for the right argument, and it has a destination of result, meaning this is the address of the instruction that it's going to send a token to. You could also have a port for that as well. but I'm not going to go into that right now. But basically, this is one possible encoding. Essentially, instead of having registers, you basically have tokens. What is the result over here? Is it ready? What is the result over here? Is it ready? And which other instruction that I'm going to send a token to? So you're going to connect these things together. So let me give you some other example data flow nodes to build a real program. So this is a conditional one. Essentially, we can implement branches over here. So what does this mean? So this is a branch node. It has a data input and a control input. And essentially what it does is it selects the value and pushes to a particular output depending on the value of the control input. So this node fires, this instruction gets fetched and executed when both the data input and the control input are ready, when you have tokens in both of these arcs. And when you have tokens in both of these arcs, what it does is if the control input is true, then it passes the data token, data value that it receives from here to the true path over here. If the control input is false, then it passes the data token, data value, to the false path. So in this case, since the control input indicated false over here, we would pass X value to the false path. That way, we've enabled some instruction downstream over here and not over here. That way, you can do an if then else statement, for example, right? Okay, another example to control the conditionals, relational. Basically, this is a comparison node, greater than node. It basically does what you expect, right? It basically fires, it gets fetched and executed when both of its data tokens are ready, when it has data values in both of its input arcs, in other words. And what it does, basically, it computes whether the value on the left arc is greater than the value in the right arc. If that's the case, it generates a true token as its output. Otherwise, it generates a false token. In this case, it generates a true token. Now we can connect this to this branch, right? Assuming that that's the relational you want, right? Okay, and then you need to, of course, do the inputs nicely. So basically, now you can do the branching, as you can see also, not just multiplication and addition, etc. You can even add more complicated synchronization primitives like barrier synchronization. I'm not going to go through the barrier synchronization in detail over here. You may actually see it in some other courses, for example, in parallel programming. But basically, what this does is this node, the goal of it is to synchronize all of the values that comes to it. Meaning, it has, let's say, three data inputs, and it basically waits for all of the three values to become available. And it fires when all of the three inputs are available. And when it fires, it basically passes the data values to the later stage output arcs. Meaning some later stage of computation gets enabled only when all of these data values are available. So that's the synchronization, as you can see. So you put this between two parts of computation that you're trying to synchronize. The first part has to finish before the second part can continue. And once you do that, you need to connect all of the outputs of the first part to the barrier synchronization node. And barrier synchronization node ensures that what you intend happens. Okay. So I've given you some examples. Now let's go through a simple data flow program. Again, if you were in class, I would ask you what it does. I will still ask you what it does. Assume that n is a non-negative integer, like 0, 1, 2, 3, 4, 5. And this is a 1 over here. What does this program do? So the inputs are n, non-negative integer, 1 over here, and then an output over here. Now, let me explain some of the nodes over here. So this means that the value, the token over here is put to the ground, meaning it's synced. You lose it, basically. You kill the token over here. And the rest, I think you almost know. Copy node is basically copying. It takes a token and it copies it onto both directions, as you can see. And then what else is not? So decrement is decrement. You get a token over here. It fires when you get a token, and you decrement the value, and then the value gets fed over here. So this notation is a little bit interesting. Basically, if initially this value is 1, but later this arc gets the value from here, and you can follow where that is coming from, right? You can see that this is coming from this part. Okay. Similarly here, initially the value of this arc is n, and later in another iteration, let's say, it gets the value coming out of this decrement. Okay, it doesn't get n again. This is in the next iteration, it gets this one. Okay, so you need to make some assumptions here that I didn't tell in detail, but hopefully This is clear. Now I think you have all the information needed to calculate what this program is doing. But let me actually pause. I will take the question while you're thinking about what this data flow program is doing, and you will tell me afterwards. Let me actually take the question. So is this model limited to computational tasks? So for example, for a task that makes something appear at a given time on screen, this sounds ineffective. How would you implement such a thing? Yeah, so that's a very good question. So I'm not going to go into the details of data flow, actually. What I will say is you can do those tasks, but you need to use synchronization operations, basically. You need to basically use some synchronization and timing operations. So you can incorporate time and synchronization into it. But that's a very good question, basically. So for computation, this is beautiful, basically. You're perfectly right. But if you are dealing with the real world, it's actually also beautiful, especially, but as long as it's asynchronous, right? As long as you don't care when something is output, it's perfectly fine. But when you're trying to really time something, then you need to put some special data flow nodes. So basically, the thinking is that you can express everything in the world as a data flow node. And if you're trying to do something that your data flow nodes don't enable you to do, create another data flow node to enable to do it. Hopefully that answers your question, but more details require a more advanced understanding of how this operates. So there's another question, branch. So what does it do? So that's the conditional that I showed you earlier, basically. That's the branch that I showed you earlier. So basically what this conditional does is, it basically takes as input this bool. And if this bool is true, it takes the value that's in its input, sends it to the true path. Otherwise, it sends it to the false path. So basically output will be output when this bool is false. So you can imagine that way. You can work through this. Okay, so now that I'm back, any answers to what this program does? Okay, somebody says, multiple people say n factorial, and they're correct, basically. Okay, let me go through it very quickly. I don't want to spoil it for people who are still solving it. So you can maybe close your ears or something, I don't know. But basically, what this program does is it takes n, and the value is 1. But let's take a look at what happens to n first. We copy n. So this node fires when n is available, and n is available at the beginning of the program, as you can see. So this becomes n. This becomes n. What this checks is if n is concurrently, the value goes here. This cannot fire, clearly, because it's not available yet. So we're going to look at this path. So if n is greater than 0, this puts a true over here. And assume that you got to give some values over here. Basically, as long as n is greater than 0, this is true. And this true gets copied over here. This true gets copied over here. So basically, as long as n is greater than 0, you're going to get the value from here passing here. And you're going to get the value from here passing here, right? So you see something interesting is happening. So initially we have 1 here. We have n here, right? So we have n, we computed n times 1 over here in the first iteration. That gets fed back here. So now we have n times 1 over here. And if you look at what happens over here, this was n. As long as this is true, meaning if n is greater than 0, that's what we're assuming over here. N goes here, gets copied. So sorry, I forgot the. I went very fast actually while executing this data flow graph. You shouldn't go this fast. Basically, what you should do is really figure out when each node gets executed, and that happens when all of its data operands, meaning all of its input arcs, have values in it. So this already had values as we discussed. So the value here is n. N gets copied over here because the input value is available. So this gives you the n minus 1 over here. Now n minus 1 goes here. So in the second iteration, we have n over here, n minus 1 over here. We repeat the same thing. Assuming n minus 1 is greater than 0, we copy it, and we pass n over here. So we multiply n with n minus 1 coming from here. Now we have n times n minus 1 over here, circulating back, and this becomes n minus 2. So basically, we keep multiplying n times n minus 1 times n minus 2, n times minus 3, etc., until n is not greater than 0. And that's essentially the definition of a factorial, right? That's n factorial. So this may not be the best way or most parallel way of implementing n factorial in a data flow machine, but this is one way. So I will let people to figure this out on their own if they're still processing it. But this is, again, the beauty of data flow. Okay. So basically, what I've shown you is a very high-level trade-off, program counter. Essentially, what is our processing model? Or do we need a program counter or a PC or instruction pointer in the ISA? If the answer to this trade-off is yes, then you get control-driven sequential execution like one Neumann did, right? And in this case, an instruction is executed when the PC points to it, and PC automatically changes sequentially except for control flow instructions. So by nature, you're restricting parallelism, right? Underneath, you can do a lot, as we will see. But by nature, at the model level, we're restricting parallelism. But if the answer is no, one potential way is doing data-driven parallel execution. An instruction is executed when all its operand values are available, and that's the notion of data flow. And this leads to huge trade-offs, basically. There are many high-level trade-offs that we're not going to cover here, but I'm going to very quickly go over them. Essentially, what is the ease of programming for average programmers or for expert programmers? Which one's easier, sequential or the data flow graphs, for example? Again, we already discussed this a little bit. In my opinion, sequential is a little bit easier, but then it could be a nurture problem, not a nature problem. Maybe we need to put more education effort into these more parallel data flow type models, right? Ease of compilation, which one's easier to compile to? Which one can the compiler reason about more easily? Again, this is a tough question, actually. Data flow may be a bit harder, potentially, because there's a lot of parallelism, but then the compiler doesn't need to extract the parallelism because the parallelism already potentially there. Performance, which one extracts parallelism better? I think data flow overall is better in terms of parallelism, as long as you're having a nice data flow graph with a lot of parallelism. And hardware complexity is another question, basically. In hardware complexity, I think the sequential models have an advantage because you clearly know which instruction you're executing, and that's the only instruction you're executing, at least at the ISA level, right? And if you implement the ISA directly in the microarchitecture, then it's very simple. But data flow by nature, you don't know what you're executing, so you have to account for the fact that you could potentially be executing hundreds of instructions at the same time, and that leads to a lot of problems. In fact, initially when data flow machines were designed, they had the problem of too much parallelism. They basically said, we designed this machine, but we don't have enough resources to execute the entire data flow graph. As a result, we have all of this overhead to put the data flow graph somewhere else so that we can execute it later, portions of it. So there's a danger over here also, too much parallelism potentially. Okay, now I've given you the ISA level or model level trade-off, whether you want to expose this to the programmer. Here we're exposing it to the programmer, right? We're programming a data flow machine, if you will. But there's a similar trade-off that can be made at the microarchitecture level as well. You can say, I want to have control-driven versus data-driven execution. So let me go into microarchitecture a little bit more. Basically, ISA specifies how the programmer sees the instructions to be executed. But microarchitecture doesn't need to care about that exactly until it touches the architectural state. Basically, microarchitecture is designed to execute instructions in some way, and that's the underlying implementation. Essentially, it's how the underlying implementation actually executes instruction. So ISA may say programmer sees a sequential control flow execution order, or programmer sees a data flow execution order. Microarchitecture can execute instructions in any order it likes, or the designer likes, as long as it obeys the semantics specified by the ISA when making the instruction results visible to the software. Basically, you can do data flow order underneath in the microarchitecture. You can do some other order depending on your constraints and goals, as long as the programmer sees the order specified by the ISA, because that's what they rely on from the machine, right, for programming and for getting correct results. So that's why microarchitecture is a bit beautiful. You can do a lot of things underneath without notifying the programmer at all. And we will see that existing machines actually do data flow type of execution. Like out of order execution is actually a form of data flow type of execution, a limited form of data flow type of execution. An out of order execution machine takes a sequential program, just like the MIPS program or SC3 program we've seen earlier. Underneath, it converts it into a data flow graph. Not exactly, but what it does is really you could construct the data flow graph that it generates, as we will see in the out of order execution lectures, and it executes that data flow graph, essentially. And underneath, it has a lot of parallelism, but it reports the results of the instructions in sequential order to the programmer and the software. So it obeys the ISA, but underneath it unleashes a lot of parallelism to maximize performance. And we're going to see how exactly that is done when we talk about out of order execution. For now, make sure the clear different distinction between ISA and microarchitecture is really clear in your heads. So, okay, we will get back to the von Neumann model. This was to really make you think, and it was important, I think. But if you really want to learn more about data flow, I would recommend, this is a seminal paper on data flow by Jack Dennis and Misunas in 1974. And people have built a lot of prototype computers. And if you really want to learn more about it, you can actually watch this lecture that I delivered about 10 years ago that goes into a lot more data flow analysis. Unfortunately, we don't have time in this class to go into data flow, but if you're interested, you can take a look. Okay, so the von Neumann model, as I said, this is the dominant model, right? All major instruction set architectures today use this model. Data flow was not successful. In fact, partially it was not successful because it came after von Neumann model took off, and basically von Neumann's paper is 1946, data flow paper 1974. You can see 28 years, right, between them. There might be some earlier paper on data flow that is not as impactful, but we don't know. At least at this point, we don't exactly know. So von Neumann model actually was very powerful, and people wrote a lot of programs on it. So it was very difficult to change the huge software stack on which systems were built. So it's very difficult for a different model to disrupt the existing software stack. And that's going to be my last point somewhere over here, but we will get to it. So basically, all major instruction set architectures use this model because it's historical. It was difficult to disrupt, and partially maybe it's because it's easier to reason about, and that's true actually partially, as we will see later on, because it's sequential and it's very easy to reason about. I'm at this program counter, I don't need to think about anything else, right? And this is the instruction that I'm going to execute. This is the next instruction I'm going to execute. Don't bother me with any other instructions that may potentially execute at this time, right? You don't need to worry about that. So that's why sequential execution and von Neumann model is very simple. And you can see there are many ISAs that use this model. Underneath, the execution model of almost all implementations is very different, essentially. Microarchitectures are very different. So we do pipelined instruction execution, which was introduced by Intel 486, for example. I'm looking at the x86 ISA over here. We're going to see that, meaning you can do portions of an instruction concurrently. That's what pipelining means, as we will see. You can do multiple instructions, execute multiple instructions at a time. Intel Pentium did this. Concurrently, you can do multiple instructions. This violates von Neumann model, as you know, because von Neumann model says sequential instruction processing. You cannot start another instruction before you finish this instruction. You can do out-of-order execution, which was introduced by Intel Pentium Pro in the x86 architecture. We have separate instruction and data caches, so we even violate the instruction and data being the same in the same memory space requirement. Basically, we do a lot of things inconsistently with the instruction set architecture underneath, but we don't expose them to the software. And that's the key. That's the key difference between ISA and microarchitecture. So let's define things a little bit. Remember that I used this definition of computer architecture earlier. This was the ISA plus implementation definition. It's the science and art of designing, selecting, and interconnecting hardware components and designing the hardware-software interface to create a computing system that satisfies some goals, basically. But the ISA-only definition was defined by Gene Amdahl, who was the chief designer of IBM 360 processors. And basically here he says that the term architecture is used to describe the attributes of a system as seen by the programmer. Essentially, whatever the programmer sees as architecture, or ISA in this case, i.e. the conceptual structure and functional behavior as distinct from the organization of the data flow and controls, as we will see, the logic design and the physical implementation. So these things are separate. You have a conceptual structure and functional behavior exposed to the programmer. Underlying data flow, control logic, logic design, and physical implementation, programmer doesn't know about it necessarily, right? Okay, so let's go a little bit more into this ISA versus microarchitecture. So I'm going to define a little bit more, but you can see also pictorially what it looks like. ISA is the agreed upon interface between software and hardware. This is what the software and compiler assumes and the hardware promises. Or in other words, what the software writer needs to know to write and debug system and user programs. Microarchitecture is a specific implementation of an ISA, not visible to the software. Microprocessor is everything in general, basically. When we talk about a microprocessor, Intel's, I don't know, Comet Lake microprocessor, you include the ISA, microarchitecture, and the circuits, right? Or the more modern definition of architecture is really the ISA plus microarchitecture, essentially. When we say architecture today, it used to mean that ISA, but today it means ISA plus microarchitecture. The way to distinguish between them is really ISA versus microarchitecture. Okay, so let's look at some examples, basically. What is part of ISA versus microarchitecture? I'm going to give you some examples later on. But let me give you an analogy first. This is similar to a car design, for example. Probably most of you drive cars or even own cars, right? Whenever you go into a car, you look for the gas pedal. Maybe you don't even look for the gas pedal. It's automatic because it's at a place that you know of, right? In most cars, at least. And this gas pedal is a great example of the ISA. Essentially, underneath, acceleration is implemented in some way, but it's exposed to the user, programmer, let's say user, the car driver, as a gas pedal. That's your interface. And you expect that gas pedal, you press it in some way, you expect it to accelerate, you take your foot off, and you expect it to decelerate or not accelerate at least, right? And that's your interface. And that's a very simple interface that you can reason about, and you know exactly how the system is supposed to behave. Underneath, each car may have a very different way of implementing acceleration, right? You may have different sorts of engines. You may have even different power mechanisms, right? Electric power could be one way of actually enabling the acceleration. Gas power could be another way of enabling the acceleration. As a programmer, you don't care about any of those. As a driver, you don't care about any of those, right? You just care about the interface. Underlying implementation can be optimized for many purposes, just like a microarchitecture does. It could be optimized for performance, energy efficiency, cost, durability, etc. So basically, the internals of the engine and acceleration, that's the microarchitecture. They implement the acceleration. So hopefully this is a nice analogy. And implementation can be various as long as it specifies a specification. Basically, there could be many, many implementations of the same acceleration function in a car, in different cars. Again, as a programmer or driver, you don't care. Again, in architecture, we have the add instruction. We saw the add instruction in our ISAs, right? How is it implemented underneath? The programmer doesn't care as long as you get an add result in the end. Of course, performance matters, right? Remember, abstraction layers, you need to really know about the underlying abstraction layers when there's a big problem underneath. So if you're not getting the performance, maybe you start caring. Assuming that you're getting the performance, you don't care about the adder implementation. You can have many different types of adders. We saw ripple carry adder, for example. We talk about the carry look ahead adders very briefly. Bit serial adders, what they can do is you can add 1 bit in 1 clock cycle. And you can do 32 bits in 32 clock cycles, right? It takes a while, but that's very area efficient. So there could be many, many trade-offs over here. Ripple carry is more area hungry, but it's faster because you actually ripple the carry. You have a chain of adders, essentially. Carry look ahead is you are actually designing customized logic to actually generate the carry much earlier. So it's much more hardware intensive, but much faster also. So clearly, there are a lot of trade-offs in the underlying microarchitecture that you can do, even for a simple add instruction, just to implement the addition function. We will see many, many other trade-offs later today and in the future. So x86 ISA, for example, has many implementations, as we have seen. And as I said earlier, microarchitecture usually changes faster than ISA because you can do stuff without affecting the programmer, without notifying the programmer in the microarchitecture, because they don't need to change anything. Underneath, you can change the adder to become much faster. Nobody needs to know this. They don't need to rewrite their programs. As a result, microarchitectures are easier to implement and change. Whereas if you want to change the ISA, that's going to be a difficult task. If you want to change the ISA completely, meaning not even preserve backward compatibility, as we discussed last time, meaning existing programs get broken, they don't execute anymore, then you have an even bigger problem, right? Then you have to enable some new software to get written in your new ISA, new instruction set architecture, and that's going to be not so easy. As a result, in history, we have very few ISAs, as you can see over here. Some of them are dead, actually, but many, 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 many microarchitectures. Intel and AMD alone have generated more than 40, 50 microarchitectures for x86 today. So there's one question that I saw over here. Does there exist any hybrid architecture which benefits from both data flow and sequential execution? Potentially, yes. And people have actually looked at this in the 1980s, 1990s. There does exist research proposals, but unfortunately, they don't exist much in real life today. Okay, so this is why I already mentioned over here, basically. ISA, when you change the software interface, it affects the programmer. As a result, it's very difficult to change the entire software stack because that requires changing the compilers, programmers' behavior, etc. But if you change the microarchitecture underneath, nobody knows necessarily, right? Okay, so let's go into more about ISA. Again, I'm not going to cover all of these over here, but ISA specifies many other things than instructions and memory and things that we discussed earlier. So it also talks about call, interrupt, exception handling. We will talk about that later. Access control, priority, privileges. We will talk about that later briefly. Input, output, task management, thread management, power management, thermal management, multi-threading support, multiprocessor support, etc. And this is an old picture of an Intel ISA manual. So basically, whatever is described as part of the thing that's exposed to the programmer in this manual is your ISA, because that's what the manual promises. And again, I'm not going to go through these detail, but hopefully this shows you the complexity of modern ISAs. They specify a lot of things that the software needs to know. This is either system software or the software that's non-system programmers write. Okay, microarchitecture, on the other end, is the implementation of the ISA under specific design constraints and goals. So anything done in hardware without exposure to software is microarchitecture. And there are many examples of this. Again, I have a laundry list over here. We're not going to go over it today, but we're going to see pipelining, in-order, out-of-order execution, memory access scheduling policy that we discussed earlier, speculative execution, whether you're executing things speculatively earlier than needed, superscalar processing, doing multiple instructions at a time, whether you're gating the clock so that if a part of your processor is not being used at this point, you don't supply the clock over there so that you can reduce the switching power. Does that get exposed to the ISA? Usually not. Caching, we will talk about caches later on. Prefetching, again, this is a form of speculative execution where you try to bring data from memory into the caches earlier so that you don't spend a lot of time accessing memory. Modern processors reduce the voltage and frequency if they're running too hot, for example, or if they have a battery life target, or if they don't need to execute intensive programs. Is that part of the ISA or microarchitecture? Now, the things become a little bit questionable over here. Again, if it's specified in the manual, if there are instructions, and if the software can actually modify the voltage and frequency or the cache in some way, then they are part of the ISA. But if these things happen underneath without software control, or without and the software cannot control it in a direct way, then that's part of the microarchitecture. Right? Error correction is some other thing that I'm not going to talk about over here. But let's do this exercise, and then we're going to take a break over here. So which one is a property of the ISA versus microarchitecture? Again, this exercise is better done in person in class, but maybe you can answer. Is this part of the ISA or microarchitecture? Add instructions opcode. I don't know if I see any results. I guess it's easier to ask these questions as we raise your hand. So some people say ISA, and they're correct, actually, because this is clearly defined by the manual, right? And hopefully this is obvious. Whether you implement a bit serial adder versus ripple carry adder. Is this part of the ISA or microarchitecture? So microarchitecture, I see a lot of, that's good, yeah. So you got the idea, basically. Number of general purpose registers. Is this part of the ISA or microarchitecture? Now I see ISAs. Okay, more ISAs, and that's correct, basically. Again, general purpose registers are specified in the manual, and in fact, instruction encodings contain the general purpose registers, so they're part of the ISA. Number of cycles to execute the multiply instruction. Is this part of the ISA or microarchitecture? How many clock cycles does it take? So a lot of people are saying microarchitecture, and that's also correct. Again, this is programmer doesn't need to know this, basically. But I will qualify this. Later, we will see architectures, instruction set architectures that require the compiler writer or the programmer to know this. These are called very long instruction word, VLIW architectures, so that they can schedule the instructions in a particular way. At that point, it becomes a part of the ISA. But in most ISAs, it's not part of the ISA. Number of ports of the register file. How many ports do you have to the register file? I guess I see microarchitecture, and that's correct over here. Basically, how many registers can you access at the same time concurrently? We didn't see the notion of ports in detail, so don't worry about it at this point. But this is, again, part of the microarchitecture. ISA, number of register operands for an instruction is a part of the ISA, because that tells you how many register operands you can have in a given instruction, for example. But ports to the register file, a completely different thing. Microarchitect can choose to have fewer ports. They can decide, for example, to use multiple clock cycles to access all the operands. So this is part of the microarchitecture. Okay, whether or not the machine employs pipeline instruction execution. You don't know pipelining right now, but essentially the idea is to execute different pieces, different stages of an instruction concurrently. And this is part of microarchitecture as well, because yes, I think people are saying microarchitecture. That's part of the microarchitecture as well. So I could keep going and going. We just exercised quickly, and thanks for participating. It was actually good, better than I expected in terms of how it would go on Zoom. But basically, I think a lot of people got everything right over here. And there will be questions on your homework and likely exam also related to this. And this is a fun part, I think. So remember, microarchitecture is implementation of ISA under specific design constraints and goals. Maybe I will cover this part and then we will take a break at an appropriate point. So design point is essentially, these are easy parts essentially. We discuss a set of design constraints and their importance. And this design point actually leads to trade-offs in both ISA and microarchitecture. So there are many example constraints as we discussed earlier. I'm not going to cover them again. Cost, performance, power, energy, availability, reliability, time to market, correctness, security, safety, predictability, etc. You basically, as a designer or as a company, let's say, you need to figure out what is important to you so that you can win customers, for example. That's your goal. And the design point is really determined by what you would like to do, the intended users and markets, the problem space, application space. For example, if you have a self-driving car, security and safety and predictability better be an important constraint and consideration in your design, right? Because if you ignore it, either you're going to cause a lot of trouble in the world, or you're not going to get a lot of customers, or I don't know, maybe there's some other option over here. But clearly, you prioritize the design point and different aspects of the design considerations and how important they are based on what your goal is in the design of your computing system. Okay, so application space is huge also, and I would recommend looking at this paper that talks about some applications as early as 2001 over here. But again, applications dream and they will appear. People will always come up with good applications and interesting applications to do something important, like genome analysis we discussed, machine learning, robotics, web search, graph analytics. This paper written in 2001 talks about scientific applications, a little bit older applications, transactions, network applications, like some real-time guaranteed delivery applications that are important. And I think self-driving cars could fit into that, for example, embedded applications, media, random software packages, etc. So applications are increasingly demanding, as we discussed, and we're going to continue to discuss that. As applications push boundaries, these trade-offs that we make are going to be even more important, basically. And trade-offs are really the soul of computer architecture, basically. We talked about ISA level trade-offs in the past couple of lectures, and today, briefly, actually longer than I expected, but as long as you learned something and started thinking critically, I'm happy. We're going to talk a little bit more about microarchitecture level trade-offs in today's lecture and later lectures. There are also system and task level trade-offs I want to mention. This is how to divide the labor between the hardware and the software. How do you divide the tasks? How do you do the parallel programming? How do you do the partitioning? How do you exploit locality, as we will discuss later? And these are also part of computer architecture, but we will not have a lot of time to deal with the system and task level trade-offs in this course. So computer architecture is the science and art of making the appropriate trade-offs to meet a design point, essentially. So why is it art? Essentially, because we do not know the future fully. There are applications, users, and market, and they're changing. Today, you're designing a processor. Your processor is going to be used 3 years down the road. It'll hit the market 3 years, 5 years down the road, maybe even 6 months down the road. But again, people can change, applications can change, and maybe it's going to be used for 30 years, 40 years down the road. So how do you actually design the system that's going to see the test of time, essentially? Because things are changing at the top, problems are changing, there are new demands, there are new issues and capabilities at the logic, circuits, and electrons. If your architecture doesn't exploit them nicely, if your microarchitecture doesn't exploit them nicely, maybe they'll become obsolete quickly. There are new demands, users change a lot, actually, personalities change. In fact, the users of today are very different from the users of 20 years ago, for example. And the future is not constant as well, basically. It changes. And we already discussed all of these changing demands. Let me quickly give some analogs from macro architecture, and then we will take a break. So future is not constant macro architecture either. This is we talked about like big architectures, right? For example, a mill can later be used as a theater, restaurant, and conference room. Churches can be used as restaurants, for example. There are a couple of examples of that in Zürich, for example. And this is one example of an original brewery that was built in late 1800s, and then it was converted to a mill partially. Now it's neither a brewery nor a mill. It's essentially an activity center, let's say. This is in Tiefenbrunn. If you have been there, you know probably. There are coffee shops, restaurants, conference centers, museum, even a fitness center, I think. This is another example. This is actually EWZ's building. They used to do electric works over here, but now you can see that it's a study space, and they actually converted nicely to a study space, as you can see over here. And also there's a coffee shop over there, and you can see some people are already studying in the study space. And if you want to know where that is, you can probably look it up. It's around Selnau stop in Zurich. So clearly these things have changed and people adapt. The question is, how can your microarchitecture and architecture adapt? Okay, so this is a great time to take a break. Let's be back at 1522, and then we're going to continue with the microarchitecture basics, and we're going to have some more fun with a real microarchitecture. I think we can get started now. I think there was a good question somewhere regarding the relationship between functional languages and compilers and data flow models, and that's a very good question actually. And I'm not going to go into details of this, but yes, there's a lot of synergy between functional languages and data flow execution models, like how immutable state is handled and how you can actually pass around arguments. So there's a lot of synergy over here, and as a result, people who worked on data flow architectures also worked on functional languages a lot and tried to merge them together in a nice way so that they could enable a lot of parallelism at all levels, if you will. But if you're interested in more on that, you can read and look at my data flow lectures that I mentioned earlier as well. Okay, now let's talk about implementing the ISA and microarchitecture basics. So we have an ISA. The question is, how do we implement it? In other words, how do we design a system that obeys the hardware-software interface while satisfying the requirements of our design point? As an aside, system can be solely hardware or a combination of hardware and software. Basically, we can take an ISA and underneath we can implement it purely in hardware, or we can do some translation to something else in software and then implement in hardware. So this is the concept of translation of ISAs, if you will. If I actually can draw over here, let's try this annotation. I'm going to draw a bit. So basically, you can have an ISA. Draw is not working well. Sorry about that. Okay, this is better, which means that I have to clear first. Draw. Okay, so you have this level. Let's assume that this is your x86 ISA, right? Well, not so nice writing. Fine. What you might do is you can take it to your own, let's say, own ISA. I don't know. Some people have done this actually. Transmeta is actually an example company that did it. Maybe Apple is doing it. I don't know. And in software, you can translate the program. In firmware, you can also do that, or you can in hardware, you can do that to this own ISA. And then this could be purely in software or software with some hardware support. And then own ISA can be executed in the microarchitecture. So this becomes control signals at this point, right? As we will see. I cannot write nicely with my mouse. This is where I need a pen, but I cannot easily present with my I guess iPad also. Anyway, this is good. So basically, you can see that there's some translation that you can do internally also. So keep this in mind. Again, I want to challenge you to think a little bit more deep. So this can actually happen also. Or you can take, this could be also hardware as well. So this part that I mentioned, the software part, that could be hardware. For example, modern x86 processors, what they do is actually, they take an x86 program, complicated instructions. Internally, they translate it in hardware to their own internal ISA that doesn't get exposed to the programmer. Basically, internally, they translate it to something like MIPS. Conceptually, it's like MIPS, actually. So what we're going to implement is going to apply very much to these complicated ISAs as well, because internally, these modern microprocessors translate the x86 ISA to something like MIPS. And then they implement MIPS like ISA in the microarchitecture. So basically, this changes the trade-offs that you make. You can take a completely different ISA and execute it on your hardware very efficiently if you can do this translation very, very efficiently, like the software, in software or hardware. So somebody mentioned Rosetta for Apple. Yes, it could be an example. I don't know exactly how it operates, but you can take x86, and if you have a very good translator over here that also can optimize the code, you can also think of this as a just-in-time compiler, really embedded into very closely to the hardware or firmware. Then you can actually do a very good job. And there are examples in the world that have done it. Okay, so basically what I just said is a virtual ISA can be converted to software by software into an implementation ISA. So this own ISA is an implementation ISA. You can think of the ISA that the programmers write code in as a virtual ISA in this case. So in the rest of these lectures, we will assume hardware implementation, but keep this in mind. So I'm going to remove this thing over here so that you can see what's written on the slides. Okay, in the rest of the lectures, we'll assume hardware implementation, but keep this translation in mind because it could be very powerful. You could be executing programs from a completely different ISA in your microarchitecture that implements some other ISA very, very efficiently, essentially, because you optimize it very heavily. Okay, so let's talk about processing and instruction. What does processing and instruction mean? Of course, we've seen many examples of this, so I'm going to go through this more quickly. But essentially, we're going to build a machine. So we never really put it formally like this, even though we showed how to execute an add, for example, a load, or even more complicated instructions, load indirect. We didn't treat it completely formally. Essentially, the formalization is that you have some architectural programmable visible state before an instruction is processed, and you process the instruction. Remember the process instruction step. It produces an architectural state prime, which is the state after the instruction is processed. This is the programmable visible state. And that's what processing an instruction means. You take an architectural state, transform it to architectural state prime, according to the ISA specification of the instruction, of course. So you need to obey the ISA while doing this. So remember, von Neumann model, we have sequential instruction processing. So this happens all sequentially, and we have the stored program computer. And remember the programmable visible state that we discussed in the von Neumann model. We have memory, program counter, and registers. There could be others, but these are the things that we're going to deal with in this course mainly. There's I/O, of course, potentially. It could be memory mapped, but I'm not going to discuss that right now. Essentially, instructions and programs specify how to transform the values of the architectural state or programmable visible state. So contrast this to a notion of microarchitectural state that's not programmable visible. You can do anything you want in the microarchitectural state space, as long as you don't touch the programmable visible space state. Basically, you can break, you don't need to obey the ISA in the microarchitectural space. Whereas these things that are programmable visible, the memory, program counter, and registers, they should be updated only based on the specification of the instruction. Okay, so this process instruction step, ISA essentially specifies abstractly what the architectural state prime should be given an instruction and the beginning architectural state. Microarchitecture implements how architectural state is transformed to architectural state prime, essentially. So if you think about an ISA, it's really a finite state machine for a given instruction. It defines an abstract finite state machine. And you all know about finite state machines from the sequential logic lecture, right? You have this abstract finite state machine where state is the programmer visible state, and the next state logic is the instruction execution specification. And your goal is really to implement that finite state machine. So from an ISA point of view, there are no intermediate states between architectural state and architectural state prime during instruction execution. Okay, one state transition per instruction, essentially. But in microarchitecture, whenever you're transforming architectural state to architectural state prime using one instruction specification, there are many choices in implementation. You can have programmer invisible state to optimize the speed of instruction execution. You can have multiple state transitions per instruction. For example, one choice is you take architectural state, transform it to architectural state prime in a single clock cycle. That's what a single cycle machine means, and that's what we're going to examine. This is simple, but we're going to see that it's really not simple in the end. It's actually a bad model, but we will see that. We'll build up to that. But this is conceptually very simple, right? It's exactly what your ISA specifies, and you do everything your ISA specifies for a given instruction in one clock cycle. But later, we will see that this is more efficient. Basically, you can take multiple clock cycles to transform architectural state to architectural state prime as described by the instruction, as specified by the instruction. What you do is you take architectural state, transform it to architectural state, plus some microarchitectural state 1. You don't change the architectural state, as you can see over here. And then in the next clock cycle, architectural state remains the same. You create some other microarchitectural state. And then in the next clock cycle, architectural state remains the same, and you create some other microarchitectural state. And the next clock cycle, you create architectural state prime. Basically, this takes some number of clock cycles to get from AS to AS prime. In the intermediate steps, you don't change AS, but in the last clock cycle, you update the architectural state prime. So from an ISA perspective, intermediate states are not visible to the programmer. So you've completely implemented what the ISA specified, but you took multiple clock cycles. Now you can optimize the clock cycle time. You can reduce your clock cycle time a lot, for example, but take multiple clock cycles to process an instruction. And you will get rid of the issues that we will have with single cycle microarchitectures as well. So underneath, you can do tricks like this, as you can see. And this is a very fundamental slide from that perspective. So basically, we're going to build a very basic instruction processing engine that looks like the first choice. AS gets transformed to AS prime in a single clock cycle given the specification of an instruction. So basically, every instruction is going to take a single clock cycle to execute. So we're going to use only combinational logic to implement instruction execution. There will be no intermediate programmer invisible state updates, meaning there will be no programmer invisible registers, for example. So basically, we're going to do this. Architectural program state at the beginning of a clock cycle. We process the instruction in one clock cycle and exactly one clock cycle. And then we're going to create or transform AS to AS prime, architectural state at the end of the clock cycle. This is very similar to a finite state machine, right? We basically say at the beginning of the clock cycle, we have the architectural state completely available to us. And for the entire clock cycle, we're going to transform it using combinational logic to some other architectural state prime. And at the end of the clock cycle, meaning at the next rising edge of the clock, this sequential logic, this register will take architectural state prime and assign it to its data values, right? Basically, architectural state will become architectural state prime at the end of the clock cycle, at the rising edge of the clock, right? And this combinational logic will implement all of the instructions that we're supposed to be able to execute, essentially. So that's what this combinational logic is. So, of course, now the question becomes, what is the clock cycle time determined by? Remember the timing and verification lecture? The clock cycle time will be determined by the longest path in this combinational logic, plus the sequencing overhead, as we discussed, like the hold time and the setup time of the latch, but ignore that for now. So you need to do all of the timing, of course, correctly to be able to make it work. But in the end, the clock cycle time will be determined by how long the longest path, the longest delay path, or the critical path of this combinational logic. And then the question, of course, is what is this critical path, longest delay path of the combinational logic determined by? And you will see that that will be determined by the longest possible instruction to execute. Because we're executing every instruction in a single clock cycle, right? Every instruction takes exactly one clock cycle. So we should be able to do every possible instruction that's specified in the ISA manual in this combinational logic, which means that this combinational logic delay will be dictated by the longest possible executing instruction. And we're going to see which one that is, hopefully by the end of this lecture, if not at the start of the next lecture. So hopefully this is clear. And this is the simplest machine, conceptually simplest machine you can build. It's a single cycle machine. But in my opinion, it's actually a very contrived design, as we will see, hopefully at the end of this lecture or at the beginning of the next lecture. Okay, so let's talk about a single cycle and multi-cycle machines a little bit more. In the single cycle machine, each instruction takes a single clock cycle. We're going to examine that in depth. All state updates are made at the end of an instruction's execution, all architectural state updates, I should say. There's a huge disadvantage. The slowest instruction determines the cycle time, long clock cycle time. As a result, you get a long clock cycle time because some instructions just by nature are very slow, right? You need to do multiple memory accesses, for example, for a load instruction, right? You need to fetch the instruction, you need to decode it, you need to evaluate the address. Using that address, you need to access memory, and then you need to update the register file, and then you're done. And concurrently, you need to update the program counter, of course. So this may take a long clock cycle time, but then every instruction needs to take that long. A very simple jump instruction that takes the program counter and concatenates it with some value, immediate value from the instruction, and updates the program counter, it can finish quickly, but it cannot know because every instruction is taking the same amount of clock cycle time, right? So there's no distinction between different instructions in this case. As a result, you cannot optimize very well. As a result, you're stuck with a very long clock cycle time. That's why single cycle machines are a bad idea. But conceptually, it's interesting to examine and it will enable us to think a little bit more and build pipeline machines, for example. Multi-cycle machines, on the other hand, they break the instruction processing cycle into multiple cycles or stages, multiple clock cycles. And state updates can be made during an instructions execution. These are microarchitectural state updates. But architectural state updates are made at the end of an instructions execution because these are visible to the programmer. So the huge advantage over a single cycle machine is that the slowest stage determines the cycle time. It's not the slowest instruction. It's really the slowest stage based on your definition of the stage as a designer. You can be a very aggressive designer and say, I'm going to break each instruction into very, very small stages, small clock cycles, essentially, right? And you can basically have a very high frequency this way. So it's important to mention that both single cycle and multi-cycle machines literally follow the von Neumann model at the microarchitecture level. They don't change the von Neumann model at the microarchitecture level. They still execute one instruction at a time, and they still do sequential execution. So they follow the von Neumann model at the microarchitecture level, but even then there's a difference between their performance, as we will see, because multi-cycle machines can optimize a clock cycle time, meaning clock frequency, much better, as we will see also. Okay, so now let's build a single cycle processor a little bit. So remember the instruction processing cycle. We have a control unit. It step-by-step processes the instructions. An instruction cycle is a sequence of steps to process an instruction. And fundamentally, there are 6 steps, as we discussed: fetch, decode, evaluate address, fetch operands, execute, and store results. And we also discussed this like this, as you can see. But remember that we said this says nothing about a clock cycle. All of this could be implemented in a single clock cycle, which means that that's a single cycle machine. Or you could take multiple clock cycles to do this implementation, and that's a multi-cycle machine. And we will see other examples that build on it later on. So in a single, so if you actually take a look at instruction processing cycle, unfortunate naming, and a machine clock cycle, a single cycle machine, single cycle refers to single clock cycle in this case. All 6 phases of the instruction processing cycle take a single machine clock cycle to complete. Whereas in a multi-cycle machine, as I said, all 6 phases of the instruction processing cycle can take multiple machine clock cycles to complete. In fact, each phase itself can take multiple clock cycles to complete. For example, if you go back to this picture, fetch operands can take 5 clock cycles. Fetch itself can take 5 clock cycles, or arbitrary number of cycles depending on where the data is. Execute can take 2 clock cycles, depending on what you're executing, right? Basically, as a designer, you have a lot of freedom in a multi-cycle machine. Okay, let's view instruction processing in another way, because we're going to make use of this way. Essentially, instructions transform data, meaning architectural state, to data prime, architectural state prime, right? This transformation is done by functional units, or in other words, units that operate on data. And those units need to be told what to do to the data, right? If you remember, when we discussed the instruction, this is a fundamental part. To enable this, an instruction processing engine consists fundamentally of 2 different components. Data path. Data path consists of hardware elements that deal with and transform data signals. For example, functional units that operate on the data, hardware structures that enable the flow of data into the functional units and registers, and out of the functional units and registers, like wires, muxes, decoders, tri-state buffers. We've seen all of them. Muxes are multiplexers, if you remember. And then storage units that store data, for example, registers, general purpose register file, instruction register, program counter, etc. So those are all data path components. Control logic, on the other hand, I mean, instruction register could be also a part of the control logic, as we will see. But control logic consists of hardware elements that determine control signals. In other words, signals that specify what the data path elements should do to the data. So how should you configure your ALU, for example? How should you configure these muxes? Which register are you reading from? Which register are you writing to? And what kind of, how are you generating the address? How should you configure the address adder, for example? And we've seen these examples, but these 2 are fundamentally different. You need to build the data path, and the data path determines what control signals that you need later on. And basically, instruction processing is really all about setting the right control signals to enable a data path to do what you really want to do to accomplish what the instruction specifies. Again, keep that in mind. Normally, when you construct a machine, you think about the data path, and you construct the data path to execute the instructions, as we will do soon. And then you basically say, oh, I need control over here. And then you decide what your control logic should be. Fundamentally, when you keep adding instructions, you keep adding data path elements, but you also keep adding control signals to enable a good use of those data path elements using your control signals. Okay, we already seen an example of this, right? I mean, this was you saw the processing unit, but really the data path is this entire thing over here. And the control unit is this mostly red part, but not all of the red part, like this finite state machine over here that is written is really the control unit over here in LC3. And we're going to get back to this picture later on. Okay, so let's take a look at how control and data are done in a single cycle machine and a multi-cycle machine. Basically, in a single cycle machine, control signals are generated in the same clock cycle as the one during which data signals are operated on. Basically, everything happens in a single clock cycle. You don't have any other clock cycle to execute the instruction. You need to generate the control signals, and also you need to use the data path elements at the same time in the same clock cycle. So you need to fundamentally serialize some processing, meaning to be able to know what to do with an instruction. First, you need to actually decode the instruction, and that needs to happen before you access the register file with the instructions bits, for example, right, to specify which operands. So fundamentally, there's some serialization that happens in a single cycle machine within a clock cycle. In a multi-cycle machine, what you can do is you have freedom, right? Essentially, you can generate the control signals needed in the next cycle in the current cycle. So current cycle, you generate the control signals and you use the control signals in the next cycle, meaning that latency of control processing can be overlapped with the latency of data path operation. As a result, you get more parallelism. So we're going to see this more clearly later on when we talk about multi-cycle machines. I'm going to show you a picture actually of how this overlapping happens. But basically, you can reduce the clock cycle time again because you can generate your control signals earlier in a previous clock cycle because your instruction takes multiple clock cycles, right? You can do things in earlier clock cycles, and then later clock cycles can be more efficient. Okay, so we're going to talk about this more, but you can, if you're interested, you can read Pat and Patel book, Appendix C, for more. These appendices should be put on the website. So if they're not on the website, you should ask my TAs so that we put them up on the website. I haven't checked the website yet, but we normally put these appendices on the website. Okay, so there are also many ways of designing the data path and control logic. So I will give you some example ways over here. So you can have a single cycle data path, multi-cycle data path, pipeline data path, and control as well. You can have single bus. Remember LC3, sorry. It has a single processor bus like this. But again, that's a design choice, right? This designer was very cost sensitive, right? Maybe you can have multiple buses, many buses, right? Separate buses that connect PC directly to this MAR. Or ALU directly to the register file, as opposed to using a single bus for everything, right? That's another design choice in the data path. You can have hardwired or micro-coded microprogram control. We're going to talk more about this. So essentially, you can have combinational versus sequential control. You can think of it that way. And that leads to some trade-offs. In the combinational control signals are generated by combinational logic. But in sequential control signals are stored in a memory structure. So you can take the instruction register and index this memory structure and get the control signals that you want. So we will see this. This is actually a beautiful way of designing machines. And we will see this when we talk about multi-cycle microarchitectures and microprogram microarchitectures later. So in the end, though, control signals and their structure depend on the data path design. You normally design a data path, and then you figure out what your control signals should be. So before we design our data path, let's do a flash forward and talk about the performance analysis, because this is going to be important. Very important, actually. We're not going to be able to get to performance analysis today, I think, given that we're somewhere in the middle of the two lectures, let's say. So execution time of a single instruction can be expressed this way. Essentially, how many cycles do you take to execute the instruction? This is called CPI, or cycles per instruction, times how long does a clock cycle take? So hopefully this is obvious, right? In a single cycle machine, CPI is always 1, and clock cycle time is long. Okay, but this is a single instruction. What about an entire program? Execution time of an entire program is you do this for every single instruction and you sum it up, right? That's the idea. Essentially, sum over all instructions executed in the program, this CPI times clock cycle time. There is a simpler way of thinking about it, approximate way of thinking about it. Well, assuming you compute the average CPI correctly, it's an exact way of thinking about it. You basically take the number of instructions in a machine, multiply number of instructions executed in a program, not in a machine, sorry, because we're calculating the execution time of a program, right? The program executes some number of instructions. You basically calculate that number of instructions times the average cycles taken by each instruction, cycle per instruction, times the clock cycle time. Okay. So this is our performance equation, if you will. This is the execution time of a program. So you can try to reduce the execution time by reducing the number of instructions, by reducing the clock cycle time, or by reducing the average CPI, in this case, as you can see, right? Okay, so let's take a look at single-cycle microarchitecture's performance and multi-cycle microarchitecture performance conceptually, looking at this equation. In a single-cycle microarchitecture, we said that CPI is 1. That's how single cycle is defined. Cycles per instruction is 1. But as we said, clock cycle time is long. And we will see that pictorially or empirically soon. In a multi-cycle microarchitecture, on the other end, CPI can be different for each instruction, right? The designer has a lot of choice. They basically can say an add instruction takes, let's say, 5 cycles to execute. A load instruction, which requires a lot of time, takes 25 cycles to execute. As a result, hopefully the average CPI is small. It's not 1, but hopefully it's small. It could be 3, let's say. Average CPI, let's say 3. But your clock cycle time can be short. So let's do some back of the envelope calculation. In a single cycle microarchitecture, your CPI is 1. Let's say clock cycle time is 1,000 nanoseconds, because the longest instruction takes 1,000 nanoseconds. Here, your CPI, let's say average CPI is 5 cycles per instruction. But if you can make your clock cycle time 20 nanoseconds, which you could, then you have 10x faster machine, right? Because this is CPI 1, clock cycle time is long, 1,000. Here, CPI is 5, clock cycle time is 20. So it takes 100 nanoseconds to execute. Of course, you need to multiply by instructions also, but I'm assuming that's constant because you're not changing the program. Then you can have an order of magnitude faster machine by doing multi-cycle microarchitecture, by keeping your clock cycle time short, because you have that freedom. Essentially, you have 2 degrees of freedom to optimize independently. You can optimize cycles per instruction, and you can very much optimize clock cycle time. Whereas here, it's going to be very difficult to optimize clock cycle time, and you've already restricted yourself to cycles per instruction 1, which is not bad necessarily compared to what we will see over here. Okay, so that was a fast flash forward. Hopefully that's interesting. You can think about how to optimize systems this way. And actually, it's a lot of fun to think about how to reduce the instructions, how to reduce the cycle per instruction, how to reduce the clock cycle time. Ideally, want to reduce all of them, right, to maximize performance, but sometimes they go against each other, as we will see later on. Okay, so now let's take a closer look at a single cycle microarchitecture and build it up. So remember, this is our single cycle machine. We're going to implement all instructions, the entire ISA, in this combinational logic. And we're going to transform, each instruction will transform some architectural state to architectural state prime in a single clock cycle. So we're going to start with some state elements to build our machine. So a program counter will look like this. And again, because everything happens in a single clock cycle, we're going to reduce the complexity a little bit. Basically, we're going to assume that the state gets updated at the end of, at the rising of edge of a clock, the program counter. So we don't need to have a write enable signal for the program counter, because program counter gets updated every clock cycle, right, at the end of a clock cycle. So it looks like this. And then we have a register file that looks like this. We have 2 input register IDs, one write register, destination register ID. That's the data that we're going to write if we write. And then these are the 2 data values that we read if we're reading. And we have a reg write signal. Are we writing to the register file? This is a control signal. So the orange signals are going to be control signals. Black signals are going to be data signals. Okay, so this is our instruction memory. We're going to assume an instruction and data memory separate for reasons that we will get to later on, but that makes it easier to just think about things. And then we're going to supply an instruction address, get the instruction. Data memory is going to be a little bit more complicated. We can supply an instruction address and read data, assuming men read signals asserted. And if you want to write data, we supply an address and the data value, and then assert the mem write signal. And then we don't read the data, of course, when we're writing. Okay, these are the sequential components that we're going to use. And this is from your book. What I showed you is actually from some other book, the Patterson and Hennessy book, Computer Organization and Design. But Essentially, both books design MIPS processors, and you'll see that they're essentially very much similar. Okay, from your book, I'm not going to go through this in detail, but I've already discussed the program counter, instruction memory, register file. You can see that register file has 2 read ports and 1 write port. You can read 2 elements at a time and write 1 element at a time. And data memory, if the write enable is 1, you can write 32-bit data, write data into memory location at 32-bit address A on the rising edge of the clock. If write enable is 0, you read 32-bit data address from A to the read port. Okay, hopefully these are simple, and you can also reinforce your learning by looking at your book, as you can see over here. For now, we're going to assume magic memory and register file. What does this mean? We're going to assume combinational read. The output of the read data port is a combinational function of the register file contents and the corresponding read select port. So basically, we're going to get the data within combinationally nicely. We don't need to write the data to a memory address register, for example, and then wait for some number of cycles. And we're going to assume synchronous write, meaning the selector register is updated on the positive edge clock transition when write enable signal is asserted. Meaning that you cannot affect read output in between clock edges. And that's exactly what we want, right, from a finite state machine, as we discussed in sequential logic lecture 6. So we're going to assume single cycle synchronous memory. Contrast this with memory that tells us when the data is ready. So this is going to be an optimistic. That's why it's called magic memory. Within 1 cycle, or even less than 1 cycle, we're going to get the data out very quickly. But usually memories take much longer, as we will see later on. So usually memories can tell us when the data is ready. So there could be a ready signal that indicates the read or write is done. But if you have a ready signal, then it's going to be more complicated to build a single cycle machine. So we're not going to do that right now. We're going to see this later on. But if you want to see it earlier, you can take a look at this Appendix C. So let's build a single cycle machine. So this is, again, from your Patterson and Hennessy book, not the Harrison-Harris or Patel Patel book. But it's going to be very similar to your Harris and Harris book in the end. So we have 5 generic steps: instruction fetch, instruction decode. So instruction fetch happens when you get the PC, input it to the instruction memory and get the instruction out. And then you decode the instruction and access the register file concurrently, operand fetch, register operand fetch. And then for instructions that are executed, you go through the ALU to get executed. For instructions that require evaluating memory address, you can evaluate the memory address in the ALU also. And then for instructions that require operand fetch from memory, you access memory. And then you store the result back to the register file. It could be from the ALU or the memory. So we're going to build a data path that essentially enables us to do this. And this is a high-level picture of the data path, actually. This is very high level, of course. It doesn't include control signals, etc. But we will, over time, include control signals soon today. Okay, so basically, we need to provide the data path plus control logic to execute all ISA instructions that we're interested in implementing. Well, let's take a look at that. So what is to come is this. We're going to build a data path that looks like this. Right now, it may look complicated. It's actually not a very complicated data path. It's a relatively simple one because it omits some instructions, as you can see over here. But we're going to build up to it. You will be able to understand exactly what everything is for. Everything is there for to execute specific instructions, basically. And you can see that the data path is in black and the control logic is in orange. Okay, so control signals are orange. They control the muxes, as you can see. They control the register file, whether you're writing to the register file. If you're not writing to the register file in this instruction, better you set that register write signal to false. They control the ALU operation. They control, for example, the muxes that determine which value gets written to the program counter next. For example, the branch instructions can control that. You can see that. They control whether you're writing data to memory. You can see that. This is well, there's mem read over here and then mem write over here, whether you're reading or writing from memory. They control whether the output, whether the data you're writing to the register comes from the memory, the ALU output or memory. So you can see that there's mem to reg signal. If this is set to 1, then the data that you're writing to memory comes from that you're writing to the register file comes from the memory. Otherwise, it comes from the register file. Otherwise, it comes from the ALU. And we will see why these are important. So we're going to build a data path to enable this. So similarly, this is the complete single cycle processor in your book. It's a bit simpler because it omits some things, but you can take a look at that also. And you're going to build something like this actually in your labs in the end. But let's now build this data path from the ground up, from scratch. Okay, so we'll start with the arithmetic and logical instructions. These are easy. So basically, how do you build a data path? You have an ISA specification as a designer. You basically say, I'm going to implement this ISA. So, and then you go and implement the ISA, right? So let's take a look at the R-type ALU instructions. Remember, these are MIPS R-type ALU instructions. They have 3 register operands. They do register-to-register signed addition. So you can see that they basically add RS to RT from the register file, and then we store the result into RD in the register file. That's the semantics, as you can see. And if mempc is equal to that instruction, meaning that if mempc, whenever you fetch the instruction, if it indicates an R-type add, this is what you do. Okay, so you need to take specific bits in the instruction, which is this encoding, use them to index the register file as register IDs, like these bits, RS bits, and then the RT bits, and then use this one as the destination register ID and do the addition in the ALU. Concurrently, you increment the program counter by 4. Okay, that's the idea. And we need to supply the data path to be able to do that, right? So you do this if the if the opcode is 0 and the funct bits, remember the funct bits over here at the bottom, specify 32. That's how your control signals will be generated, right? Okay, but before we generate the control signals, let's take a look at the data path. So we're going to implement this over here, general purpose register RS plus general purpose register RT. You add them, and general purpose register RD gets that value, and PC gets incremented by PC plus 4. Let's add the PC gets incremented by PC plus 4 by 4 data path. This is it. You have a special adder. You hard code to 4. You get the value of the PC, add to it 4, write the result back into PC. And this happens in a single clock cycle, basically. While that's happening, let's do the general purpose register addition. Well, before that, we need to actually read the instruction at the program counter. So we have the instruction memory. This gives us the instruction after some time. We use some of the instruction bits to determine RS, RT, and RD. Okay. RS and RT give us the read data. That takes some time. And basically, we set the ALU operation to be add, and we get the results. That takes some time. We connect it to the right data, and we ensure that the reg write signal is 1. At the end of the clock cycle, the write register indicated by bits 15 through 11 in the instruction, which is RD, is going to get the right data value produced by the ALU result over here at the rising edge of the clock, at the end of the single clock cycle that our machine has. So that's the data path, basically. This is all the data path you need to execute this instruction. And the data flows, as you can see, right? You read the instruction, you decode it slightly, and then you access the register file, you get the source operands, you do the addition by controlling the ALU appropriately. The results gets written right in the write back stage, let's say, phase of execution processing, because you set the control signal correctly, and the data gets written to the write register that is specified by the instruction bits you can see over here. Okay, so that's our R-type ALU data path, and you can clearly see how you can control the ALU. ALU operation comes from some control logic that needs to decide what bits should be provided to the ALU, what 3 bits should be provided to the ALU so that it can do the addition. I'm not going to go through this in detail as we discussed earlier. So let's take a look at how we can extend this data path to I-type ALU instructions. Remember, I-type, they add a register, source register, to assign extended immediate that comes from the instruction. And that's the only difference. Everything else is essentially the same. Well, of course, the opcode is different, etc. But that's how it is. So let's take a look at the data path over here. Essentially, PC plus 4 data path is the same. We read the instruction, and write register, read register IDs are the same. Now, what we need to do is we read data 1 over here. We read the source register, but the second operand to the ALU should be sign extended 16-bit immediate from the bottom 16 bits of the instruction. So that's why we need to add the data path here and add it to ALU. ALU operation is still add over here, and then the result gets written to the destination register, as you can see. So we need to set the reg write signal to 1 again. But the only difference is this. The ALU operation is really, the input of the second ALU data input is really sign extended 16-bit immediate as opposed to register over here. So if you want to use the same data path that we built for R-type instructions. For I-type instructions also, you just need to add some muxes. Well, I guess there was one more difference that I kind of ignored over here, because let's take a look at this mux over here. So basically, if the instruction is I-type, we added this mux. If the instruction is not I-type, it's R-type, we basically take the register file output and input it into the ALU. If the instruction is I-type, we take the sign extended 16-bit immediate and input it into the ALU, as you can see over here. So we have another control signal that we need to control. That's called the ALU source. Now, unfortunately, there was also some distinction in the instruction encoding. So you can see that the RT register over here is the destination, not the RD that used to be over here in an R-type. So we need to actually have the destination register ID correct in the register file also. So if it's I-type, the destination register ID comes from bits 20 through 16 of the instruction register or instruction bits. Otherwise, if it's R-type, then the destination register ID comes from bits 15 through 11. So that's the idiosyncrasy of the ISA. You need to obey what the ISA says clearly, and that introduces some more muxes. Multiplexers, clearly that introduces more delay to this path also, right, as you can see. But if you want to implement R-type and I-type in the same data path, now we've done it. This is our data path for R-type and I-type ALU instructions. And if you remember in LC3, we had something similar, right? Actually, if you look at LC3 data path, this is our add, assembly, and machine code. You don't need to look at that, but you can look over here, right? This is our ALU. ALU can take two input operands. One comes from the register file directly. The other comes from the output of a mux. And this multiplexer takes values from either the register file to do a register-to-register add, for example, or the sign extended immediate. And which one to use is determined by the instruction opcode. Or not the opcode, extended opcode. It's basically a bit in the instruction. So you can see the ISAs, even though the ISAs are slightly different, the data paths are similar, right? This part of the data path is exactly similar, actually, as you can see. Okay, so let's take a look at a single-sided data path for data moment instructions. So load instructions. This is going to be essentially similar to what you've seen earlier also, but we're going to extend the data path. Essentially, this is a load word. And again, we increment the PC, and the specification is base plus offset. We take the general purpose register in the base over here, RS, indicated by RS. We add to it a sign extended offset to calculate the effective address. And we use that effective address to index memory and get the data from memory and put it into general purpose register specified by RT. Ignore the translate step. We'll talk about virtual memory later, but translation is something that we do, but that'll complicate the data path, but ignore it for now. So load data path is also simple. Basically, we're going to extend the data path that we saw earlier. So clearly PC plus 4, we already have it. Let's calculate the effective address first. Essentially, to calculate the effective address, what do we need? We need the base register. So the base register, so we need the data path to read register 1. So the value is here. We need to add to it sign extended offset. So we already have that, sign extend offset, right? So essentially, we set is I-type to 1. So we already had everything that we needed almost, because we implemented the I-type instructions. So we basically take this first register value, set this mux to is I-type 1, such that it takes actually the sign extended 16-bit immediate offset from the instruction. Now ALU gets us the address. We connect that address over here to memory. And then the memory, we're not writing to memory, so we set this to 0. We're reading from memory, so we set this to 1. And the data appears, read data, and we need to put it back into the destination register. That's the idea. So there needs to be some connection over here. So I will connect that later on in a little bit. But I guess if we have to do it right now, let me try to annotate. This annotation is basically what we need to do is in the data path, do this, right? Okay. So that enables us to do the load word right now. Okay. But let's take a look at store again, store before, so that we can complete the load and store data path together. So what store does is, I guess I need to clear this. Wow. Okay. So to be able to do the store, essentially we need to do very similar things. PC plus 4, of course, every instruction does it almost. And then we calculate the effective address exactly the same way we calculate it for the load. But instead of writing to a general purpose register, we reverse this. We write it to memory at the effective address from the general purpose register specified by RT. Okay. So to be able to do that, what do we do? So to enable store, this is the store word data path. Again, we need to read the register. that to base register, we need to add to it essentially the sign extended offset, and that gives us our address. And we need to get our write data somehow, and that comes from the register file. So let me actually annotate over here so that you see clearly. I should change the color also maybe. So let's do it over here. Basically, this is our address, ALU result, and we need to get the data from the register file and write to memory, right? And we're not reading from memory, so this doesn't need to be connected anywhere for the store. We're writing to memory for the store, so this needs to be 1. And we're reading from memory, as you can see. We're not reading from memory. That's why this needs to be set to 0. And everything else is very similar to I-type instructions, because we're writing to a register specified by RT, just like the I-type instruction. Okay, let me clear this. Now let me finish the store and load data path together, and then we're going to stop. So basically, if you want to do store and load together, you basically combine the data paths. But you need to be very careful in terms of the control signals, in terms of how you set the control signals as well. But this is our load store data path together. So you can see that if an instruction is a store, you enable the mem-write signal. If an instruction is a load, you enable the mem-read signal. You clearly connect the second register output of the register file to the write data, but you don't use it in a load. Address is used for both and stores, and that needs to add the register file's first input to a sign extended immediate coming from the instruction. We don't write to the register file if the instruction is not a store. We write to the register file only if the instruction is a store. And the destination register is also if it's I-type. Okay, so basically this is the complete data path. There's one thing that I omitted over here. If you want to actually execute the ALU operations as well as stores, they both write to the register file, right? The question is, if you want to execute them in the same data path, the data coming to the destination register could come from the ALU results here, or it could come from memory if it's a store. So you need to provide another multiplexer basically to enable this. And this is essentially what we did over here compared to the previous picture. So the previous picture looks like this, load store. Now we add non-control flow, although basically essentially all ALU operations as well, R-type. So if the data is coming from, if the destination register data is coming from ALU's results, that happens if it's not a load. Then you need to select, you need to set up the control signals for the mux multiplexer such that you select the ALU results and pass it to the write data port of the register file. If it's a load, then you need to set up the control signal mem to reg to 1 such that it selects the data that's coming from the memory and that gets written to the register file. Okay, so hopefully this was interesting. This is a good place to stop because control flow will actually add a little bit more complexity. If there are any burning questions, I can take them now. Otherwise, we're going to stop. Any questions? Okay, so I think basically have a good weekend and have a nice break. We're not going to have lectures tomorrow or the next week, but we will continue with this single cycle microarchitecture and build up to multi-cycle and pipelining after Easter. So have a nice break and hopefully you'll recharge nicely and stay safe.